Start with something that has nothing to do with prime numbers. Add up 1 plus 1/4 plus 1/9 plus 1/16, and keep going down the squares forever. That sum settles on a number a little past 1 6/10. Nothing about it looks unusual. You are just adding smaller and smaller fractions until they stop mattering. Now put that aside and look at the primes instead. 2, 3, 5, 7, 11, 13. The numbers that refuse to break into smaller factors. They are scattered along the number line with no obvious rule, thinning out as you go, and nobody has ever found a clean formula that prints them in order. These two things, a tidy sum of fractions on one side and the ragged list of primes on the other, belong to completely different corners of mathematics. One is smooth and predictable. The other is the textbook example of disorder. In 1737, a young Leonhard Euler wrote down a single equation with the sum on one side and the primes on the other, and showed they were the same thing. Not similar. Equal, exactly, for every value you plug in. That one line is the reason a sum that never mentions a prime can hand you a fact about every prime at once, and the reason a constant from circles is hiding inside the primes. By the end of this, you will have built that equation yourself and watched both surprises fall out of it. Let's make the orderly side precise, because we are going to need to steer it. Take a number, call it s, and form the sum 1 plus 1 over 2 to the s, plus 1 over 3 to the s, plus 1 over 4 to the s, on through every whole number. When s is 2, the bottoms are the squares, 1, 4, 9, 16, and the total is that 1 6/10 we just saw. When s is larger, the terms shrink faster and the total is smaller. As long as s stays bigger than 1, the tail dies off quickly enough that the whole thing adds up to a finite number. This sum has a name. It's called the zeta function, written with the Greek letter, and you feed it one number and it returns another. The one feature to keep in mind is right there in the definition. Every whole number from 1 upward shows up exactly once on the bottom of exactly one fraction. 1, 2, 3, 4, 5, none skipped, none repeated. That total ordinariness, every integer present and accounted for, is the only property of this sum we will actually use. Hold on to it. It is the hinge the whole argument turns on. Now the other side, and here is where the primes walk in. We build it one prime at a time, starting with the smallest. Take the 2, form the little sum 1, plus 1 over 2 to the s, plus 1 over 4 to the s, plus 1 over 8 to the s, marching up the powers of 2. Each term is a fixed fraction of the one before it, so this is a geometric series, the kind with a clean closed value. At s equal to 2, that fraction between terms is 1/4, and a geometric series that shrinks by 1/4 each step adds up to exactly 4/3. So this whole infinite tower over the powers of 2 collapses to one tidy expression, 1 over the quantity 1 minus 1 over 2 to the s. That collapse is worth pausing on, because it is the engine of the whole thing. An endless sum over all the powers of a single prime folds up into one short fraction built from that prime. You can check the folding by hand. 1 plus 1/4 is 1 1/4, add 1/16, and you are at 1 5/16. Add 1/64, and you reach about 1.33, already nosing up against 4/3, which the geometric formula says is the exact limit. Do the same for the 3, and you get 1 over the quantity 1 minus 1 over 3 to the s. For the 5, 1 over 1 minus 1 over 5 to the s. One neat factor per prime, each one secretly an infinite sum over that prime's powers, waiting to be unpacked. So now do the obvious thing. Multiply those 1 per prime factors together, all of them, over every prime at once, and ask what you get. Unfold each factor back into its infinite sum and multiply the sums out. A term in the product is built by reaching into the 2's box and grabbing some power of 2, reaching into the 3's box and grabbing some power of 3, and so on, then multiplying your picks. The fractions you can build this way are exactly 1 over a power of 2, times a power of 3, times a power of 5, and onward. But that is just 1 over a number written in its prime factorization, and every whole number, has exactly one prime factorization, no more, no less. So every fraction 1 over n to the s appears in the product once, and only once, for one and the same reason that 12 is 2 times 2 times 3 in only one way. There is a cleaner way to feel the same fact, running it backwards as a sieve. Start from the full sum over every integer. Strip out the factor for the 2, and algebraically it deletes every term whose bottom is even, every multiple of 2 gone in one stroke. Strip out the factor for the 3, and every remaining multiple of 3 vanishes too. Keep striking with each prime, and the only term that survives the whole gauntlet is the 1 over 1 at the front. The primes, working together, sieve the entire number line down to nothing but the number 1. Put the two halves together, and the equation is finished. The sum over every whole number, the zeta function, equals the product over every prime of 1 over 1 minus that prime to the minus s. The left side never mentions a prime. The right side is built from nothing but primes. They are the same number for every s bigger than 1, and Euler proved it in 1737, working in St. Petersburg, decades before anyone had a clear idea of why the primes are spaced the way they are. The proof is exactly the unfolding and multiplying we just did, with unique factorization doing the real work. This is the bridge the whole video promised, and it earns its keep immediately. Because the two sides are equal, any honest statement about the sum becomes a statement about the primes, and the other way around. A question about a smooth, well-behaved series turns into a question about the most stubborn objects in arithmetic with no translation cost. We are going to send exactly 2 facts across that bridge. First, what happens as s slides down toward 1. Then, what happens when s sits at 2. Push s down toward 1 and watch the sum side first. At s equal to 1, the bottoms are just the plain whole numbers. 1 plus 1/2 plus 1/3 plus 1/4, the harmonic sum. And that sum is famous for having no ceiling at all. It crawls upward without ever stopping, past 10, past 100, given enough terms. So the left side of the equation grows without bound as s approaches 1, but the two sides are equal, which forces the product over the primes to grow without bound in exactly the same way. Now suppose, just to test it, that there were only finitely many primes. Then the right side would be a finite product of finite numbers, a plain fixed value, which cannot run off to infinity. It does run off to infinity. So the supposition is dead. There must be infinitely many primes. That is Euler's own proof that the primes never run out, and it is a completely different route from the old one about multiplying a list and adding one. His is analytic. It hears the primes through the size of an infinite sum, and it says something sharper as a bonus. If you add up not the primes themselves, but their reciprocals, 1/2 plus 1/3 plus 1/5 plus 1/7 and onward, that total also has no ceiling. Up to 10 it is about 1 3/10, up to 1,000 about 2 2/10, up to 100,000 only about 2 7/10, creeping up roughly like the logarithm of a logarithm, painfully slowly, but never settling. The primes are thin, yet not thin enough for even their reciprocals to converge. Now leave s at 2 and send that across instead, because this is where a circle turns up where it has no business being. The left side at s equal to 2 is the sum of the reciprocal squares, the one we opened with, and Leonhard Euler had already proved 2 years earlier in 1735 that it equals pi squared over 6. That is the famous Basel result, pi. The ratio from circles, dropping out of a sum of fractions with no circle in sight. Set that equal to the product side, and you get a startling sentence. The product over every prime of 1 over 1 minus 1 over that prime squared equals pi squared over 6. A quantity assembled out of nothing but the primes comes out to a simple expression in pi. And you do not have to take it on faith, because the product converges fast enough to watch. Multiply the factor for the 2, and you are at 1 1/3 well short. Bring in the 3 and you reach 1 1/2. The 5, the 7, and you are climbing toward the target. By the time you fold in every prime up to about 200, the product sits at 1.6437, and the true value is 1.6449. The gap is already down near 1,000th, and shrinking with each new prime. The primes really are conspiring, term by term, to reproduce pi squared over 6. That hidden pi is not just a curiosity on a chart. It controls an honest probability you could test with dice. Pick two whole numbers at random, as large as you like, and ask whether they share any common factor bigger than 1. Sometimes they do, like 6 and 15, which are both divisible by 3. Sometimes they have nothing in common, like 8 and 9. The chance that they come up with no shared factor, that they are co-prime, works out to exactly 6 over pi squared, which is about 0.6079, a little over 60%. The reason is the equation again. Sharing the factor 2 has probability 1 in 4, sharing a 3 has probability 1 in 9, and the chance of dodging every prime at once multiplies into 1 over the same product we just evaluated, which is 1 over pi squared over 6, namely 6 over pi squared. The cleanest way to believe it is to just run the experiment. Take 200,000 random pairs and count how often they turn out co-prime. Early on the running fraction wobbles, but it homes in fast. At 1,000 pairs it sits near 0.597, at 50,000, 0.61. By 200,000 it is 0.6086, against the predicted 0.6079. The dice agree with the circle to 3 decimal places, and there was never a circle anywhere in the question. That is the whole point of the bridge. A fact about random integers, carried over the equation, arrives wearing pi. So step back and look at what one equation brought us. On the left, a smooth sum over every whole number. On the right, a product over the primes. Set them equal, and a question about the harmonic sum becomes a proof that the primes never end, while a question about the reciprocal squares becomes pi squared over 6 hiding in the primes. And from there, the odds that two random numbers are co-prime. None of those facts share a topic on the surface. The equation is the only thing that connects them, and it connects them perfectly. If you remember one thing, let it be that an equal sign between a sum and a product let a constant from circles leak into the most disorderly objects in arithmetic. And the same equation opens a door that is still wide open today. Euler only ever needed s to be a real number bigger than 1, because below that the sum stops adding up to anything finite. About a century later, in 1859, Bernhard Riemann allowed s to be a complex number, extended the zeta function past that boundary, and asked a single question: where does it equal 0? The answer would pin down, more precisely than anything else known, exactly how the primes thin out as you climb. It is the Riemann hypothesis, and after more than 160 years nobody has proved it, though it has been checked for many billions of cases. The bridge Euler built in one line, between a sum and a product, is still the main road into the deepest unsolved problem about the primes.